Welcome to Lecture 8, 1.2, Applications with Linear and Rational Equations. Alright, so we're moving into the word problems, or another word for it is applications. So one thing that's really important, and I will be checking for this on your exams, for all application problems, the following work needs to be shown. As usual, I think I mentioned before, the final answer is not going to be what you're entirely graded on. It may be worth only 1 point. What matters is the work you show. Which is nice because even if you make a mistake somewhere, if you show work and it looks like you know a lot what you're doing, but for example, maybe you missed a minus sign or something, you'll get most of the credit, depending. So for application problems, you always need a let statement for the variable. For example, that would be if you said, let x equal the height of the house. Maybe. Okay, so you have to let the reader know what your variable stands for and what are you solving for. There is sometimes you can just use a drawing to indicate what the variable represents, either a diagram or something like that. If you have one of those, you don't actually need to write a let statement, but you need to indicate where your variable is on the diagram. For example, if we're looking at the plot for a house, you might say x is this side of the house, and then x plus 3 is the length. So with that, you wouldn't have to write a let statement, you just leave your diagram. And then I can see your diagram and say, oh, I know what x represents. After that, you need to have an equation for solving. Then show work for solving your equation. And finally, write your answer in a complete sentence. That includes a capital letter and a period, or you could use an exclamation point if you feel excited. Okay. Why do we need to write our answer in a complete sentence? Well, we're in college, so hopefully you're able to communicate to me what you're solving for and why. And also, why do I need a capital letter and a period? Once again, we are in college. That's good form. If you go into any form of a job, most employers want to see you know how to write a complete sentence. Alright, so keeping that in mind, I will be checking for all 4 of these. And most word problems are worth around 10 points. So normally, your let statement, possibly worth about 1 point. Your equation, possibly about 2 points. And then in solving the equation, that's about where the bulk of the points come from. Final answer is 1 point. So that leaves about 6 points for solving the equation. So that's normally how I set up problems. It will vary a little bit, but that's about a good idea on how I set up word problems. At least for the editing and grading. So now let's take a look at one of the first word problems. There are different types, and I've just broken these up into the different types. So the first one we're looking at are ones involving simple interest. We'll look at ones that involve like compound interest and all of that when you get into Math 135. But for Math 103, we're just looking at simple interest, which means the problem is thankfully simpler. Alright, so Kealoha borrowed, that should be borrowed, a total of $22,000 from 2 different banks to start a business. One bank charged the equivalent of 4% simple interest, and the other charged 5.5% interest. If the total interest after 1 year was $910, determine the amount borrowed from each bank. Alright, so what I like to do is I use a certain sort of a box chart to set up my work. Other teachers have different ways to do it, but I'll go ahead and show you my method, and you can decide whether or not you like it. But as usual, you just need to show me a let statement and an equation. So this is going to help us get both of those. So how I label this is interest, capital I for interest, equals principal times the rate times the time. Alright, and for all of our problems in this class, our time is always going to be 1 year, unless otherwise indicated. Alright, so let me go ahead and fill out these boxes for interest, principal, rate, and time. And then we're going to set this up because we have 2 different percentages we are looking at. Or 2 different amounts borrowed, actually. So there is from Bank 1. I'll call this one Bank 1. And then the other one was Bank 2. Bank 2. So Bank 1, Bank 2, shorthand. Okay, so what was the interest? Well, we know that the total interest after 1 year was $910. So these 2 guys should equal 910. And we don't actually know what they are, so I'm going to leave that blank for now. Let's go ahead and look at the principal. What is the principal? That's the amount you put in, or the amount you borrowed. So, in this case, Caleb had borrowed $22,000 from 2 different banks. Well, how do I know how to combine them? Well, you know what I'm going to do? I'm going to say, I don't know how much Caleb had borrowed from Bank 1. I don't. I'm going to call it X. So how would I figure it out how to represent the amount borrowed from the next bank? Well, it'll just be the 22,000 minus X. And that'll give us however much they borrowed from Bank 2. Okay, so here algebra's coming into play. And then the rate. Well, for the first bank, the rate was 4%. Second bank, the rate was 5.5%. And the time, as usual, I said, was just 1 for these problems. So, the last box is always, or pretty much always, going to be the box you use to create your equation, the last one you fill in. So what do we know about this box? Well, it is P times R times T. So P is X, R, well, we can't use a percent in an equation, so we're going to go ahead and make that into a decimal. So 0.04x, and then times 1. Anything times 1 is itself, so we'll kind of leave out the 1. So then the other box is going to be this times this. Once again, we're going to turn that percent into a decimal, so it's going to be 0.055. So 22,000 minus x times the 0.055. Kind of squishing that in. Okay, so now we're going to use these two to write our equation. Well, how? Well, this is the interest from what you borrowed from Bank 1, and this represents the interest of what you borrowed from Bank 2. And we know that in total, that amount is $910. So the interest from Bank 1 and the interest from Bank 2 is $910. I can turn that into an equation. Is the same thing as equals in math. Let's write down the 910. And then and means addition in math. Well, what is the interest from what you borrowed from Bank 1? That is 0.04x. And what is the interest from Bank 2? It's right there. Ooh, I might have run out of room on this one. Let me go ahead and erase that. So writing it in, minus x times the 0.055. All right, let's write that out a little neater. Now, I kind of want to get rid of all of the decimals. Okay, so to do that, let's go ahead and multiply everything by 100. Notice this is one term, so they all get multiplied by 100. When I do that, the decimals disappear. I'm left with 4x plus 22,000 minus x times 5.5. Well, we didn't manage to fully get rid of the decimal, but that's okay. We'll go ahead and work with what we have. You could go ahead and multiply it by 1,000 if you wanted to get fully rid of the decimals. But let's get rid of those parentheses by distributing in. And we'll have 4x plus the 22,000. Oops, let's go ahead and do that multiplication. 5 times the 22,000. 22,000 times the 5.5 minus the 5.5x because 91,000. All right, now we want to go ahead and combine like terms. On this side, we have the 4x and the negative 5.5. So we have negative 1.5x plus the 121,000. Now we're solving a linear equation. Let's go ahead and subtract the 121 from both sides of the equation to get x by itself on one side. And let's see, what will we get when we do that? We'll get negative 30,000. Okay, and you can divide that. Let's see, we have to divide both sides by the negative 1.5 to get x by itself. Let's continue this equation up here. And then we have x equals 20,000. Okay, we solved for x, but what does x mean? We can't just box our answer and leave it. This is a word problem. X, what we said earlier, was the amount borrowed from Bank 1. So how do we find out the amount borrowed from Bank 2? Well, it's just 22,000 minus x. 22,000 minus x. 22,000 minus x, which is actually what we found right there, the 20,000. That's just going to leave us with 2,000. And that's how much you borrowed from Bank 2. So what would we say? Okay, Aloha borrowed 20,000 at 4% interest. And 2,000, oops, I forgot the unit on the other one. To go ahead and write my dollar sign for my unit, very important, at 5.5% interest. All right, and there we go. That would be my answer. Okay, that box chart often works well. So, the next one we have is applications involving mixtures. Mixtures tends to be one of the more simple and straightforward problems because they always sort of follow the same pattern. So what do we have here? A nurse mixes 60 cc of a 50% saline solution with a 10% saline solution, which should produce a 25% saline solution. How much of the 10% saline solution should he use? Okay. So, let's just draw an image. He has some amount, right? And he's adding together another saline solution. What do we know? He has a 50% saline solution, and he's adding to it a 10% saline solution. And what does he want? He wants a 25% saline solution. How much of each was he using? For the 50%, he uses 60 cc. For the 10%, we don't actually know how much. And we don't know how much is the 25%. But actually notice, our question here says how much of the 10% should he use? And oftentimes, in algebra, the variable is what we don't know. So good idea is to check what the question is, and that often is going to be the variable. So the 10% is going to be our variable. I'll go ahead and call it n this time. Why not? N cc's, we don't know how many. So how would we label the amount up there? Well, that is just going to be 60 plus n. We don't know how much it is, but we can say it's 60 plus n. Okay, so the way we set it up for mixture problems is pretty much in this exact same manner. You have the amount, so the number, and the percent. And then you multiply the two together, and you basically copy this exactly down to get your equation. So we'll have the 60 times, oh, and we can't use a percent. So this time I'm going to use a fraction. 50 over 100 plus, bring down that plus, n times 10 over 100 equals, remember these parentheses, these are very important, it's 60 plus n times the 25 over 100. Okay, I have my equation. Let's clear out those fractions. So we're going to go multiply both sides of the equation by 100. When I do that, this 100 will distribute to both and cancel out the 100, and that 100 cancels with that 100. So we've cleared the fractions, and we have 60 times 50 plus 10 times n. I swapped them around, it's perfectly fine. Equals 60 plus n times 25. And I'm going to do my best to line up the equal signs as we go along. Let's see, 60 times 50. I'm just going to leave that for now. I'll do 50 times 60 plus 10n equals. Now let's get rid of that parentheses on the other side. Let's use distribution with the 25 to the 60 and the end. So we have 25 times, oops, that looks like 28. 25 times 60 plus 25n. We're solving a linear equation. Let's go ahead and get the n's on one side. So to do that, this time I'm going to go ahead and put the n's where they're going to be positive. So I'll subtract 10n from both sides. Let me use a different color. And then I'll go ahead and subtract the numbers to the other side. $25 minus 10 is going to be 15n. Alright, so I'm going to show you a trick here. This has to do with the same way we treat variables. I have 50 60s, and I'm taking away from it 25 60s. So 50 minus 25 means I have 25 60s left over. 15n. That's a shorthand. If it was a little too much for you, you can go ahead and multiply it out and work that out. Okay. Now let's go ahead and divide both sides by 15. Let's see. 15 and 25. They're both divisible by 5. 5 left over, 3 left over. 3 can go into 60. Cancel that. 20 left over. So in the bottom, we only have 1 left over. And in the top, we have 5 times 20. Let's carry our equation on over here. So 5 times 20 is going to be 10. Add on that other 10. 100 equals n. Okay, we can't just box our answer and say we're finished. What does the n stand for? That's the amount of 10 cc we're using. So how much 10 cc should we use? We should use 100 cc of the 10%, 10% solution, saline solution. As always, the units are very important. Make sure to include units like money, saline solution, miles, things like that. Okay, let's take a look at the next problem. Example 3. There are some errors in my problem. I'm going to edit those on the notes that I upload to La Lima, so bear with me on this. Example 3. Piggy competes in a biathlon by running and bicycling around a large loop through the city. She runs the loop 1 time and bicycles the loop 5 times. Period. She can run 8 miles per hour and she can ride 6 miles per hour. If the total time it takes her to complete the race is 1 hour and 45 minutes, determine the distance of the loop. Alright, well, let's see. Let's draw a diagram here. We have a loop. I'll just go ahead and make it look like a track, maybe. Okay. And she's bicycling and riding around it. But we don't know how long it is. We don't know the distance of the whole thing. Since we don't know what it is, we'll say it's x. So, let x equal distance of the loop. Alright, so one of the main keys here to notice about this problem is we're talking about miles per hour. Once you hear the terms miles per hour, often you're working with a motion problem. And for motion problems, the formula we use is distance equals rate times the time. And I'm going to go ahead and use that to look at the distance, rate, and time of both her biking and her running. So I'll say R for running, B for biking. We're looking at the distance, the rate, and the time. Now, once again, the last one we fill in, last one of these boxes we fill in, very similar to the interest one, is probably going to be the one we use for writing our equation. So what do we know? Well, we see this pair of information, and often there's a pair given. 8 miles per hour and 16 miles per hour. So that's for the rate. So for running, she can go 8 miles per hour. And for the biking, she can go 16 miles per hour. Alright, what else do we know? Well, we know that she runs through the loop 1 time, and she bicycles 5 times. So the distance for running would just be going around it once, so that would be x. And the distance for bicycling would be 5 times. So she went around 5 times, so that would be 5 times x. So the distance for biking would be 5x. Okay, so the last box we have to fill in is the time. And that's what we're going to be using for our equation. How do we fill in t? Let's look at our equation here. D equals rate times time. I want to solve for t. So how do we get t by itself? Let's go ahead and divide both sides by r. which means that d divided by r is t. So oftentimes with motion problems, you'll use this little trick of solving for your variable. So we have that there, which means filling in these two boxes, we'll just take the distance and divide it by the rate. So the distance is x divided by the rate, 8. Distance, 5x, divided by the rate, 16. So we're going to use these two to create our equation. We know the total time is 1 hour and 45 minutes. Let's see, in a word problem, we have to be careful here. When we're using time in our equation, it's in terms of hours. We have to translate minutes into hours. To do that, you'll get the 45 divided by 60, and you'll get 0.75. So 1 hour and 45 minutes is 1.75 hours. Once again, we're going to translate this to an equation. We have the word is. That'll be my equal sign. Now let's see the total time. Well, that's the amount of time she took walking or running plus the amount of time she took biking, which would be x over 8 plus 5x over 16 equals 1.75. And there we have our equation. So let's see, to add these two fractions, I'm going to go ahead and use the building up property to create 16 as a common denominator. I want to get to one fraction. So I have 2x over 16 plus 5x over 16 equals 1.75. Let's add these two. They now have the same denominator. So we have 2x plus 5x all over 16 equals 1.75. Carry on over here. We can go ahead and add those two to get 7x over 16 equals 1.75. Getting rid of the 16 in the denominator, we'll multiply both sides by 16. That cancels. We get 16 here. 1.75 times 16 is 28. So we have 7x equals 28. Now solving for x, let's go ahead and divide both sides by 7. And 28 divided by 7 is 4. But remember, it's a word problem. What does that mean? That is the distance around the track. So the distance of the loop is 4, is this miles or kilometers? Well, since they're talking about miles per hour, we're going to be doing with miles. So 4 miles. Make sure to include your unit, like miles or whatnot. Don't just say the distance of the loop is 4. Okay, be sure to use your units. Okay, let's take a look at the next problem. Solve the application involving a rate of work done. Example 4. Josh and Lonnie can wash the windows of the house together in 30 minutes. When Josh works alone, it takes him 50 minutes. How long would it take Lonnie to wash all of the windows by herself? So for a work problem, what we're going to know how to do is use the work box. Oops, that looked ugly. Alright, work box. We're going to do the amount of time Josh worked, Lonnie, and then T for together. So what we do is we do the total time, which we would do either in hours or in minutes. So you have to make sure when you're working with these types of problems, stick with either hours or minutes. Don't split between one person doing it in hours and the other in minutes. Okay, so we're going to take a look at the rate. Okay, so the total time. Well, it takes Josh 50 minutes alone. Lonnie, we don't know. Well, whatever we don't know, that's going to be our variable, right? That's what we're trying to figure out, how long it'll take her. So that'll be my x. Or you could make it another variable as long as you indicate what it is. And then T stands for the time together, which was 30 minutes. All right, the rate, you just take the reciprocal. 1 over 50, 1 over x, and 1 over 30. Easy thing about work problems is it's always these guys working together equal to the total. So you take Josh's rate, add it to Lonnie's rate, and that'll equal the total work rate. So now we have fractions added together. Let's go ahead and clear the fractions. So to do that, let's multiply both sides by what is the lowest common denominator. Looks like it's going to be 150. So multiplying both sides by 150, this will get multiplied in. Then I get 150 times 1 over 50 plus 150 times 1 over x equals 1 over 30 times 150. Let's see what cancels. 50 and 150, we have 3 left. Oh, we forgot something. We need to include the x for the common denominator. The x wouldn't cancel here. Let's go ahead and throw in the x. Okay, so now we have the x. Good. X cancels to that x, and then the other denominator cancels, 30 and 5. That's a good way to check to make sure you did the common denominator correctly. If something doesn't cancel, you did it incorrectly. So we have 3x left. Oop, wrong color. Plus 150 equals 5x. Add 3x to the other side to get the x's by themselves, because we're solving a linear problem. Oops, wrong one. Let's erase that. Okay. Minusing 3x from both sides. Divide both sides by 2. And we get 75. So what did x stand for? X was the time it takes Lonnie to wash the windows by herself. And what was the units? It's minutes. So it would take Lonnie 75 minutes to wash the windows. And if you want to be really thorough, you can say by herself. All right, there we go. And boxing our answer. So the next problem we have is solving applications using proportions. So this one often has to do with setting up two fractions equal to each other. Let's take a look at this one. A student 5 feet tall measures the length of the shadow of the Washington Monument to be 144 feet. What is the Washington Monument? It's that tall sort of, I think, obelisk type thing, if that's the right word for it. Out in Washington, okay? Has all the flags around it and everything. Okay, so it has a sort of a triangular top. And then, a student is 5 feet tall, measuring the length of the shadow. So we have the shadow of the object, right? The sun's at some angle. We have the shadow of the object. And the student right here, this is totally not to scale. The student right here is measuring her own shadow. And what do we know? Well, we know the student is 5 feet tall. And the Washington Monument is 444 feet. Oops. 444 feet. Running out of some room. I have a little tab on the side I need to work with. All right. And let's see. So we had the 444, 5 feet tall. Okay. Her shadow. Oh, I wrote this wrong. That's not the height of the monument. That's the height of the shadow, or the length of the shadow. 4 feet. Her shadow is 4 feet. Oops. These little things right here are just indicating that's the length. We want to find the height. All right, remember the question is all pretty much often, or most often, where your variable comes from. So x, height of the Washington Monument. What is the height? We're going to use here the concept of similar triangles. We're going to assume, because these people are standing up straight, we got sort of a right triangle thing going on here. And we know, proportionally, that if you take the proportion between these two, or the ratio between those two sides, it's equal to the ratio between the other two sides. 5 and 4. We're relating these two using ratios or proportions. Okay, we have our equation. Let's go ahead and solve. We can go ahead and use cross multiplication. because we have a fraction equal to a fraction, which means we have 444 times 5 equals 4 times x. We could multiply this out, but let's not do that. Why? Because when I divide the 4 from the x, I can simplify these. 444 divided by 4 would just be 111, which means I have 111 times 5 equals x. 111 times 5 is going to be 555 equals x. And what was x? X was the height of the monument. So the monument is 555 feet tall. And I googled that, and apparently that actually is the height of the Washington Monument, which is kind of a neat random fact. Alright, so you can impress somebody with that someday. Okay. Solve applications involving geometric shapes. Example 6. A contractor must tile a rectangular kitchen that is 4 feet longer than it is wide, and the perimeter of the kitchen is 48 feet. Find the dimensions of the kitchen. Let's get a visual here. Alright, we have a kitchen. It's rectangular. Sort of a shaky rectangle there. And it's 4 feet longer than it is wide. Well, I know nothing about the width, so I'm going to let that be x. But I know that the length is 4 feet longer than x. So that's just going to be x plus 4, because it's 4 feet longer. If you were 4 feet taller than me, and I was 6 feet tall, you'd be 10 feet. Just add the 4. And what else do we know? Well, we know the perimeter is 48 feet. Now we're trying to find an equation here to be able to solve for the dimensions of the kitchen. And we can use the concept of the perimeter and the fact that we know the lengths. So let's see. Perimeter is all the areas, or all the sides added up. Or perimeter for a rectangle would be 2w times 2l. W for width, L for length. Well, what's the width? It's x. And what's the length? The length is x plus 4. Let's go ahead and throw those in. So we have P. Oh, what is P? What is the perimeter? The perimeter is given. It's 48 feet. Let's throw all of those in. So we have 48 equals 2 times our W, which is x, plus 2 times our L value, remember the parentheses, x plus 4. Let's rewrite that. So 48 equals 2x plus 2x plus 4. Let's go ahead and distribute to get rid of those parentheses. We have 48 equals 2x plus 2x plus 8. Continuing on the side, 48 equals... Now I'm going to go ahead and add these two like terms together. That'll give me 4x, so 48 equals 4x plus 8. Now let's solve for x. To get x by itself, subtract 8 from both sides. And we get 40 equals 4x. Lastly, to solve for x, divide both sides by 4. 40 divided by 4 will just be 10. So what are the dimensions? Well, let's see. X was the width, and x plus 4 was the length. So the dimensions are 4 or 10 feet by 14 feet. How did I get the 14? I just did 10 plus 4. Because remember, x equaled 10. Alright, the next part of the problem. How many square feet of tile should be ordered if the contractor adds an additional 10% to account for waste from cutting the tile? Well, we want how many square feet? Let's see. How would we figure out how many square feet we need? Well, to find the number of square feet, what you do is you look at the dimensions and you multiply them together to get the area. Well, 10 times 14 is going to be 140 square feet, or feet squared. So those are dimensions. We need 140 feet squared. But we need 10% extra to account for waste. So to find that, what we need is the 140 plus 10% of 140. Well, 10% of 140 is just going to be 140 times 0.1. And this is going to be the amount of square feet needed. So what do we have? 140 plus 140 times 0.1. Moving the decimal over, we get 14. So that'll be 154. Alrighty, so how many square feet do we need? We need 154 square feet. Of tile. Or you could say we need to order 154 square feet. Next is to determine the total cost if the tile cost $12 per foot squared and the sales tax is 6%. Okay, so let's see. Well, we know we need 154, and each square foot is $12, which means we want 154 times 12, but we have to add on to that the sales tax, which is going to be 6% of whatever this is. So that'll be 154 times 12. We need to multiply that by the sales tax, which is 0.06. Okay, so once again, this is the amount from actually finding out the cost of the tile, but as usual, we have to pay taxes, so this is 0.06% of the amount we're getting. Just like if you went and bought a Spam musubi at 7-Eleven when I was a kid, a Spam musubi was like $1.05, and then taxes was like, no, I think it was $1. And taxes was around 5 cents. So even though the musubi was 99 cents or $1, I'd end up paying $1.05 because of the cents added onto it. Okay, so you have taxes. So what do we get here? 154 times 12. 1,848 plus the 1,848 times the 0.06, which is our taxes there. That ends up being $110.88 in taxes. Ugh, wow, that's a lot of money in taxes. Plus the 1,848, and we get the grand total right there. Okay, so what do we write as our answer? The total cost for the tile is, remember our dollar sign or a unit, 1,958.88, period. Alright, there we go, and that is it for our application problems.